Hi and welcome back everybody to MrMiers Math channel. Today in Algebra 2AB we're going over Chapter 8, which is talking about exponential and logarithmic functions. And in particular in Section 8.3 we're going to be talking about modeling with exponential functions. So our goal is to write models for exponential growth and decay. And not only that, but we're also going to make a prediction with some of those models, because after all, that's kind of the point of mathematics. To uncover some fundamental characteristic of the universe, maybe see a pattern that occurs in nature, and then use that pattern to make a prediction. That's kind of the point. All right, so let's get into what we're talking about in terms of models with exponential functions. Now, I do have to preface that the models that we're going to be talking about are very, very basic. So basic exponential growth and decay models. All right, we always want to start out with something basic, because then after that, if we're trying to liken this to something that's happening in the real world, we can add things to it and make it model a little bit more closely the situation that we're trying to deal with. But we always want to start with something that's rather simple. So some real life quantities increase or decrease by a fixed percent each year or other time period. All right, the amount y of such a quantity after t years can be modeled by the following two equations. All right, if that thing is modeling exponential growth, we could use y equals a times the quantity 1 plus r to the t power, or exponential decay uses y equals a times 1 minus r to the t power. So that 1 plus r is what we call the growth rate. Okay, whatever this quantity is in whole is what we call the growth factor. And then in terms of exponential decay, that 1 minus r is going to be what we call the decay factor. Remember, factors are what we're multiplying by. So when we say growth factor and decay factor, we're talking about this entire quantity. All right, what are we continuously multiplying by? All right, in each one of these. So A is the initial amount, like we've talked about previously in the last two sections. So that's like our starting amount when t equals 0, where are we at? So that's the initial amount. R is the percent increase or decrease. Now just to note, like if we were talking about a 25% increase or decrease, remember we can't just put 25 in here. We've got to put it in decimal form. So that would be 0.25. Okay, and then t would be the number of time periods. So we'll talk about that in some of the different situations that we go over. So let's get to the next example. All right, in example 1, we just want to determine whether the function shows exponential growth or exponential decay. All right, then we're going to identify the initial amount and the percent increase or decrease. Now, in terms of figuring out whether it's exponential growth or exponential decay, that could be very easy. All right, in part A, we can see that it's going to be exponential growth because we're adding something to 1. So that value that we're continuously multiplying by is going to be greater than 1, causing exponential growth. All right, whereas in part B, that value that we're going to multiply by, since we're subtracting 0.2, is going to be less than 1. All right, 1 minus 0.2 would be 0.8, so this would decay over time. All right, and then the initial amount, remember that is A, that comes right here, right before that growth or decay factor. All right, so A, or the initial amount in part A would be 14. The initial amount in part B would be 82. And then finally, the percent increase or decrease. That is what we're adding or subtracting to 1. So we're adding 0.4 to 1. Now, 0.4 isn't the percent increase. Remember, this is written in decimal form. We got to change that to a percent. So really simple way, move that decimal point over twice, and we get 40%, or multiply it by 100. 1 minus 0.2, the 0.2 is going to be that percent increase or decrease. So this is going down, and we just have to change this into percentage, right, which would be 20%. Now in part C and D, we can see these growth and decay rates. It doesn't say plus something or minus something. It's just giving us the growth rate and the decay rate. So either way, we just have to figure out, is that number greater than 1? If yes, it's growth, like in part C. If no, it's decay, like in part D. All right, the initial value is just still going to be that value right before. 175 is that initial value here. 14 is the initial value in part D. And then finally, for the percent increase or decrease, we're not going to use the whole 1.6, okay? We're going to have to just use the 0.6. How much is it over or how much is it less than 1? So it's 0.6 over 1, which would be a 60% increase over each time period. All right, 0.9, if we just do 1 minus 0.9, we'll get the difference, which is 0.1. So that would be a 10% decrease, which is causing that exponential decay. All right, awesome. Let's get to our first example using a mathematical model. All right, so one year a clothing company had $1.5 million in sales. In later years, sales Y in millions of dollars increased by about 25% each year. So once again, we're always going to be talking about really simplistic models here. Maybe in later days we can complicate things a little bit more that for those that actually want to go into the weeds with some of these real life examples. So we have $1.5 million in sales, and it's increasing by 25% each year. We want to write an exponential growth model that represents this situation. So the sales after T years. All right, so to write that exponential growth model, and if, there we go, my pen comes up, here we go. Remember that's y equals a times 1 plus r to the t power. Okay, so somewhere in here we have a and we have r. A is the initial amount. All right, so that's the amount that we start with. So that would be the 1.5 million. And then r is the growth rate. That would represent that 25%. And remember, we have to change that into a decimal, so that'd be 0.25. All right, so we could represent the sales after T years as y equals 1.5. Remember, this is going to be in millions, so y is in millions, so we don't have to write out 1.5 million, times 1 plus r to the t power. Of course, we could leave it like this. We could also simplify. 1 plus 0.25 would be 1.25. So the simplified version of this equation would be 1.5 times 1.25 to the t power. Now, of course, the whole point of actually building a model to represent some scenario would be to use it to make some kind of prediction. All right, we want to use the model to predict the sales after 8 years. All right, so that's the time period. All right, so we can just plug in 8. So that's 1.5 times 1.25 to the 8th power. All right, now you can type it into your calculator exactly as shown, and that thing is going to work. All right, if you got a TI calculator, you got a Casio calculator, that's all going to work. If you're doing it on your phone, it depends on the type of phone that you have. So if you want to make it really easy, just to make sure that you don't have any mistakes, especially if you're not very comfortable using the calculator that you have, we're going to type in 1.25 to the 8th power, press enter, and then multiply by 1.5. All right, that's going to work no matter what calculator you have. Okay, for some interesting calculators, you might actually have to type in the power first, and then type in the base and press enter. Okay, but for most, that's going to work. All right, hopefully you know what you're doing with the calculator that you have at home. All right, so that would give us 8.94 million. Remember, this is in million. All right, $8.94 million by the end of 8 years. Once again, really simplistic model. Obviously, in any real-life scenario, this is probably not going to be the case. All right, there's going to be many other real-life factors that come into play that would change that value, and that's something that we can talk about at a later date. All right, so now let's move on to the next example. All right, in example 3, you buy a new computer for $1,500. The value Y in dollars of the computer decreases by 40% each year. Write an exponential decay model that represents the value of the computer. use the model to estimate the value after 3 years. All right, so in part A, once again, we want to write an exponential decay model. So just going to rewrite what we had on the previous slide. Our exponential decay model is y equals a times the quantity 1 minus r to the t power. So we have to figure out what is r and what is a in the equation. A is the initial amount, so that would be our 1500. And then since it's decaying, we're subtracting, and 40% would be 0.4. So we have 1 minus 0.4 to the t power. Now once again, I'm going to simplify this. Y equals 1500 times 0.6 to the t power. Now one thing to consider is for t, in terms of time, okay, if we think about it, we have some limitations here. So I'm going to just add a simple limitation. All right, we're not going to go back in time here. We're just going to look at what happens from now to then. Okay, so that would mean t is going to be greater than or equal to 0, and that's the only part of the function that we're actually going to consider. We're not going to consider the full function where we could input some negative values. All right, if we want to use the model to estimate the value after 3 years, we're just going to plug 3 in. So that'd be 1500 times 0.6 to the third power. All right, hopefully you know your calculator best. Let's type this in, and we get about $324. So after 3 years, that computer, by these estimations here, would be a value of $324. Obviously, a huge loss. Now, technology does decrease in value pretty significantly, but maybe not that significantly. 3 years, $324. Maybe you could get a little bit more out of it. Who knows? All right, the last part of this question that we're going to talk about is actually graphing the model. So I'm going to pause really quickly, and then we'll talk about graphing the model. All right, and we're back, and I just wanted to pause that really quickly to make sure that our graph on the screen is all right and okay to use for this example. It's okay, it's not the best, but we're going to use it anyway. So what we're going to do is we're going to make a little table just like we did in previous examples in the last 2 sections. And we're going to start with 0. All right, so here's our time, and then here's our value. And in the graph, we're starting with 0, and we're just going to consider just year by year. So I'm actually going to go 1, 2, 3, all the way up to, let's say, 10. All right, and in our calculator, we can figure out what these values are for each one of these individual input values. Remember, our function was y equals 1500 times 1.6 to the t power. So if we input 0, we'd have 1500 times 0.6 to the 0th power, which would be 1500. All right, when after 1 year, that price would go down to 900. After 2 years, 540. After 3 years, 324, 194 and 40 cents, 116, 64, 69.98, and so on. I'm just going to fill in the rest all the way up to 10. Okay. Obviously, after 10 years, I think you could get a little bit more than $9 out of it. But who knows? Never know. I'm sure you could go on some social media and get something more than $9 out of it after 10 years, hopefully. But now what we're going to do is we're going to plot this on the graph. Like I said, the graph isn't the best, but it's still usable, and we can get some a good picture of what's going on. All right, so first where we want to start is with the initial value, 0, 1500. Now we have to figure out what to go up by. All right, and I'm just going to have each one of these tick marks be 100, and I'm just going to mark every 3 Okay, so there's 300, 4, 5, 600, 7, 8, 900, 11, 1200, and we got one more, 1500. All right, so there would be our very first point. But now on the horizontal axis, once again, we got to figure out what to go up by so that there's enough space and that it's spread out a little bit. I'm going to go up by 1 every single time and just mark every other. So there's 2. You know, instead of that, actually, I'm going to go back. We've got enough space here to say every 2 is 1 year. How about that? There's 2, 3, 4, 5, 6, 7, 8, 9, and then 10. All right, obviously this is going to skew what the graph actually looks like if we used our graphing calculator or something of that sort. We could get a picture as to what this actually looks like without the skewed scales. But this just makes it nice and neat, and you can see what I'm doing here. All right, so we have 0, 1500 as the first point, and I'm going to continue to plot the rest of the points to the best of my ability, and we're just going to estimate. All right, it doesn't have to be 100% accurate. That's okay. If you wanted 100% accuracy, you could probably go with some simulation, some graphing calculator, or something of that sort. Now we have 2, 540. There's 500 right here, so 40. Let's say it's about right there. Oof, my tablet's a little off here, so just bear with me. So 3, 324. Okay, 4, 194, just below 200. 5, 116. 6, 69.98. 7, 41.99, and so on, and I really can't even tell the difference now because it's so darn close to 0. All right, so just graphing what we have. Wow, that might be the best graph I've ever drawn. I don't know. We can see that decaying over time, and this would be in the case that it decays by 40% each year. It's craziness. All right, let's move on to the next one. All right, now let's talk about compound interest. So compound interest is interest paid on initial investment called the principal and on previously earned interest. Interest earned is expressed as an annual percent, but interest is usually compounded more than once a year. Okay, we'll talk about compounding quarterly, compounding continuously, things like that. And once again, this is just a basic example of compound interest. In real life, things get a little bit more complicated than that. So initial principal P is deposited in an account that pays interest at an annual rate R expressed as a decimal, compounded n times per year. The amount A in the account after T years can be modeled by this formula. So A equals P times the quantity 1 plus R on N to the NT power. Whew. So N is the number of times it's being compounded per year. Okay, so that's something that we're going to consider when we get to this next example. All right, so let's say we deposit $2,000 in an account that pays 2% annual interest. Okay, and let's also say that this thing gets compounded quarterly. Now, if we think about what quarterly means, all right, a quarter is 25 cents. Right, in terms of our imperial system in the U.S. All right, 25 cents. It takes 4 quarters to make $1, 1 whole dollar. So that means quarterly would be 1/4. So 4 times every single year. All right, that's what it means to be compounded quarterly. So we can just write N equals 4. All right, for the balance after 10 years, 10 would be the time. And of course, we have our initial investment, which is $2,000. And then it pays 2% annual interest. R, remember, is not 2. Okay, it would be 0.02. All right, that would be the annual interest. Now, just inputting those values into our equation, we would have A equals 2,000 times 1 plus 0.02 on 4 to the 4 times 10 power. Whew. All right, so that's A equals P, the principal. I should have that initial amount. Remember, we were supposed to call the principal. Sometimes I get caught up calling it A, the initial amount. The principal equals 1 plus R over N to the NT power. That's how we're getting this equation. Now we just have to use order of operations to help us solve this thing. So 0.02 over 4. I'm going to start with that first. 0.02 over 4 would be 0.005. All right, if we add that to 1, that would be 1.005. And then 4 times 10 would be 40. So we have 2,000 times 1.005 to the 40th power. Okay, and that would give us approximately $2,441.59, okay, after those 10 years. All right, so we earned $441.59 in terms of interest if we earned 2% annual interest compounded quarterly over those 10 years. Now let's say it was compounded monthly, so every month, all right, this thing would get compounded. So that would be 12 times in a year. All right, so after 12 times in 1 year, that would change these values dramatically. So we have 1 plus 0.02 on 12 times 12, or sorry, to the 12 times 10 power. Okay, for some reason I did not do this in the calculator beforehand, so I'm going to do that right now. Just get my calculator out. All right, and I got 2,442.40. Yay, so we got about almost $1 more. Awesome. All right, now that was compounded quarterly and compounded monthly. Let's say we wanted something that was compounded, let's say, continuously. All right, when something's compounded continuously, the interest is calculated as if an infinite number of compounding periods occur each year. That's what's called compounding continuously. So it's continuously tacking on that interest. All right, how we could write that equation would be A equals P times e to the RT power. All right, now e is a number. All right, so that is not another variable. That's something to keep in mind. When you're looking at your calculator, you should have a value with that lowercase e on it that represents that number. All right, so that's something that we're going to have to make sure to use. All right, let's see how this affects things in the next example. All right, you deposit $500 in an account that pays 4% annual interest compounded continuously. All right, find the balance after 1 year. Okay, well, we can just write down the equation. A equals P times e to the RT power. So P is 500, the principal. R would be 0.04. So we have 500 times e to the RT power. And t in this case is just 1 year. All right, if we type that into our calculator, we get approximately $520.41. So we earned $20.41 on interest over that year. That's not bad. All right. If it was just sitting in that account, I'll take the extra $20.41. That sounds good to me. All right. The next thing that we're going to do is um, figure out what the graph of this function looks like. I'm going to clear the board. All right, so like before, we're going to create a table of values, and I'm going to do that on the right side, and then we're going to have to figure out what we want to scale this graph. All right, so we have t, which is our input values. That is the time. I'm going to do the same thing as before. I'm just going to look at 0 through 10. All right, and keep it simple. All right, and then we're going to find the amount, okay? So if we plug 0 in, we would get 500, which would make sense. We started with $500, and then after 1 year, we would be at $520.41. Okay, $541.64, $563.75. $586.76, and so on. I'm going to write down the rest of these values here. All right, and as we're approaching 10 years here, we get about $745.91. So after 10 years, that would be a profit of, or earning interest of $245. All right, that's not too bad. Now we're going to graph this, but before we do so, we got to set our scale. Now I'm going to change this a little bit. The time is going to remain the same. All right, so on the x-axis, where we have t, every 2, I'm just going to write down 1. That way we can space this out a little bit so my ugly handwriting doesn't get all bunched up together. All right, and then on the other axis, essentially the y-axis here, we have a, and I'm going to go, let's see, every 2, I'm going to say that's about 100. So we're going to go up by 50s. Just taking some time here. Here we go. And I don't have to go all the way up here because obviously by 10 we only get to 745. So I'm going to leave it right there. All right, so at 0, we're at 500. All right, about 520. 541. 563. 586. Let me pick up the pace here. 610. 635. 61. Right there. 688. 716. 745. Okay. Now we're going to draw this graph here, trying to follow those points that I drew. Now, of course, on this graph, as you notice, with the scaling changes that have been made here, this looks pretty linear. Okay, but it is not linear. If we graphed it with normal scales, it would look like exponential growth. All right, we'd see a little bit more of that curve that's occurring. Um, Now the whole question was estimate how long it will take the money to grow to $700. So we're going to use our graph to estimate this. So first $700, that's right here. We're going to take a look at where approximately that intersects with our graph. Well, that's pretty darn close to 9. Let's say about right here. And maybe it's pretty close to 8.5, I would say. So approximately 8.5 years. All right, folks, so that was a little introduction to exponential models with real-life examples. All right, so if you like that, hit the like button, subscribe, and thank you, and have a good day.